All right, so the problem last night was, first of all, to write all the dissociation equations and predict a titration curve for HF, and you were supposed to label for the equations to indicate the represented theory. So hydrofluoric acid is HF. HF is one of the weak acids, and we stated that you can tell when you have a binary acid that it's strong when the anion part, the back part here, is one of the halogens other than fluorine. So since this is a binary acid and it doesn't have one of those anions, then this must be a weak acid. Okay, so we're going to dissolve it in water. The first dissociation equation will be using the Arrhenius theory. Arrhenius. And it just simply dissociates when you put it in water, and we represent it in this fashion. I will in a minute, yeah. And because it is a weak acid, you use a double arrow. Okay? Because what's really happening, the way we often state it is that it doesn't dissociate completely. In reality, it dissociates completely, but not all at one time. It's kind of a better way to put it. Okay? If you say it doesn't dissociate completely, that's what makes it a weak acid, that's acceptable. But I want you to understand, in theory, the reason it seems not to be dissociated completely is because, in fact, it only dissociates completely at different times. So you have a forward reaction going on or a reverse reaction going on, so you can't completely get rid of all of this. It never completely goes away. You have a little, some of this, mostly this actually, mostly this actually, and very little of this. So that's the Arrhenius theory. The Bronsted-Lowry theory then makes water part of the chemical equation or chemical reaction. So in that case, hydrofluoric acid actually reacts with water, and so the hydrogen is going to dissociate as it did here. It dissociates, but then Bronsted-Lowry looks at what does it do after it dissociates, and it's going to go over here and join up with the water. The hydrogen ion, which has a positive charge and wants to have 2 electrons, is going to covalently bond with one of the 2 lone pairs on this oxygen, and we get hydronium. And we still get the same fluoride anion. Okay. If we're going to write a titration curve, since this is a weak acid, we're going to start somewhere above 0 here, because typically speaking, weak acids never quite get to a pH of 0. We're going to start with a concentrated solution of HF. Off the screen a bit. Here we go. And we're going to add to that base solution. As we add the base solution, this is our independent variable. So what we are changing is the amount of base solution added to our sample of concentrated hydrofluoric acid solution. And we're going to watch, as a result, the change in the pH. So it's going to start somewhere above 0. I'm just going to pick there. It doesn't really matter where you pick there because you wouldn't know. But you should know that you're going to get this long plateau before we start to get the cliff face. Okay? And that's the buffering region. And then so after that you get a cliff face, and then you get this. And it never quite reaches 14. You don't have to have a dotted line there, but it never quite reaches 14. I probably should have it closer to 14 than that, because a strong base would bring it closer to 14. All right, so this is an acid titration curve. I would label this as the buffering region. Since we have a weak acid, there's always a buffering region. And sometimes there's more than one buffering region. We've got an equivalence point here. And the equivalence point is going to be at the steepest part of the cliff face. So what's really happening is we have a curve that's sweeping upward, and even though you can't tell, if you look at it very, very closely, it starts to sweep to the right again. So when it changes the inflection from sweeping up to sweeping over, that's the equivalence point. Okay? And I think that's pretty much everything that I expect you to do. Any questions about all of that? Why not?
Yes, please do.
You want me to? Okay, good.